The holy grail of clean energy is no longer a distant dream. It is now closer to reality. Something thought to be science fiction till a few decades ago is actually turning out to be reality.
Imagine a power plant that drinks seawater, breathes air, and spits out steady, clean energy with almost no long-lived waste. Sounds like sci-fi, right? Yet engineers have chased this dream for decades, and the race is suddenly getting wild. Today, we're stepping onto a construction site so complex it looks unreal, where humans are trying to copy the heart of the sun. We'll explain what nuclear fusion is, why it keeps slipping away, and how one small private US startup is catching up with giants faster than anyone expected, and the world is watching from lab to grid. The fusion promise. Fusion is the process that powers the sun. Tiny atoms slam together and become a heavier atom. In that squeeze, a little bit of mass turns into a lot of energy. In power plants today, we mostly use fission, which splits heavy atoms apart. Fusion flips that idea. It joins light atoms, usually forms of hydrogen, and aims to release energy without the same kind of long-term radioactive waste. The fuel is also hard to run out of. Deuterium can be taken from water, and tritium can be made inside the reactor from lithium. If you could make fusion work in a controlled way, you could run huge cities with far less carbon pollution and with far less fuel transport. That is why governments and companies keep funding it, even after decades of slow progress. But fusion is not a single gadget. It is a whole system. You need fuel, heat, pressure, and time all at once. You need a way to pull energy out as heat, make steam, spin turbines, and do it safely every day. You also need a design that can be built, repaired, and paid for. The dream is simple, the engineering is not. Enter the startup. Now the story takes a sharp turn. While the big international project crawls forward, a small, privately funded US team has been moving fast. Instead of betting on a machine the size of a stadium, this group is betting on better hardware. The key idea is simple. If your magnets are stronger, you can make the whole reactor smaller while still holding the plasma tight. That is where new superconducting magnets come in. Superconductors can carry huge currents with almost no resistance, which lets magnets reach insane strength. For a long time, the best superconductors had to be cooled close to absolute zero and were hard to shape into useful coils. Newer high-temperature superconductors still need deep cooling, but they can work at warmer temperatures than older materials and can handle higher fields. That extra margin changes the design space. It can turn a giant machine into a compact one. A compact approach has huge construction benefits: smaller buildings, shorter cable runs, fewer tons of steel, and faster assembly. It also helps investors because you can build a test reactor sooner, learn faster, and iterate. Private funding also changes the culture. Decisions can be made in days, not years, and teams can redesign parts between builds. Of course, the risk is higher because there is no single government treasury to fall back on. But if the tech works, the reward is a real path from prototype to a fleet of plants. That speed is why the startup is suddenly in the same conversation as projects backed by governments. It is not that physics got easy overnight, it is that the tools improved, and one team is taking full advantage of it, building the machine. Even with a smaller design, the site is still intense. You do not just pour concrete and bolt together a reactor. You build a clean, controlled factory around it. The floor has to be flat and strong enough for heavy lifts. The walls have to shield sensitive work from vibration. Every crane move must be planned, because many parts are heavy, fragile, and expensive. At the heart of the build is the vacuum vessel, the sealed chamber that holds the plasma. It has to be leak-tight, smooth, and precisely aligned, because the magnets and internal structures all reference its shape. Wrapped around it are the big field coils, often assembled like a giant puzzle. Some coils may be built in segments, tested, and then joined, because shipping a full coil can be harder than making one. Then there is the cryogenic system. Superconducting magnets only work when they are cold, so the reactor needs powerful coolers, insulation, and pipes. It is a strange contrast. You are building a machine that makes star-like heat, but you must keep key parts near deep freeze. On top of that come power supplies, control rooms, diagnostics, and safety systems. Sensors watch the plasma shape, temperature, and stability. Fast computers react in real time to prevent a disruption. All of this means fusion progress is tied to industry. If suppliers can make better tapes, stronger joints, and cleaner welds, fusion gets closer. If they cannot, the schedule slips. So every build is also a test of modern manufacturing. Why it's so hard? Here is the brutal part. To get fusion, you must push the fuel to extreme conditions. Hydrogen atoms repel each other, so you need very high heat to make them collide. We are talking about temperatures hotter than the core of the sun. At that point, the fuel is not a gas, it is plasma, a soup of charged particles. Plasma does not want to sit still. It wriggles, it leaks, and it crashes into walls. That is why most fusion machines use magnets. Strong magnetic fields act like invisible rails that steer the plasma away from the metal. In a common design called a tokamak, the plasma is shaped like a ring, like a glowing donut. Other labs use different paths, like twisting stellarators or firing lasers at tiny fuel pellets. The goal is the same in every case. Keep the fuel dense and hot long enough for the reactions to snowball. People often hear about a single experiment that produced more energy than it used. That can be true in a narrow sense, but a power plant has a tougher test. You must count every watt that runs the magnets, the heaters, the pumps, and the cooling systems. You must also repeat the result again and again, not once. Even when the physics works for a moment, the materials are punished. Fast neutrons blast the reactor walls. Magnets must stay cold while sitting next to something hotter than anything on Earth. Every pipe, weld, sensor, and bolt has to survive heat, radiation, and vibration. So fusion is not just a science problem. It is a construction problem, a manufacturing problem, and a quality control problem all at once. The giant in France. For years, the biggest symbol of this effort has been a massive international reactor being built in southern France. It is the kind of project that makes even other mega projects look small. Thousands of workers, parts shipped from all over the world, and a schedule that has to align across many countries. The machine is designed to prove that a tokamak can produce far more fusion power than the heating power that starts it. It is not meant to feed electricity straight into the grid. It is a scientific step that comes before a true power plant. The size is not just for show. Bigger plasmas are often easier to keep stable, and the heat has more space to spread out. But scale comes with pain. When you build something that large, every delay is expensive. Every mistake is slow to fix. A single component can be the size of a house and still need millimeter level precision. Even moving parts around site becomes a special operation, with custom cranes, special transport frames, and tight safety rules. This is why fusion has a reputation for always being 20 or 30 years away. These machines are hard to design and even harder to build. Still, the giant reactor matters because it creates a shared test bed. It pushes industry to make new materials, new magnets, and new methods that the rest of the field can use. What success would mean? Let's say this compact reactor works. What happens next is just as important. You still need to turn fusion power into electricity. That means capturing heat, most likely with a blanket that absorbs energy and also breeds tritium fuel. It means managing neutron damage and swapping out worn parts, like a mechanic changes brake pads, but with robots inside a hot, radioactive chamber. It means proving the plant can run for long stretches, not just for a headline moment. Yet the payoff would be enormous. Fusion would complement wind and solar by providing steady power when the weather changes. It could cut the need for fossil backup and reduce the pressure on long-distance fuel shipping. It could also help heavy industry, where high heat is hard to decarbonize. That is why governments watch these startups closely, and why private money is flowing in. there are also hard limits to remember. Fusion will not be a quick fix for climate change on its own. Even the most optimistic plans require years of testings, Sakhalin licensing, and grid integration. Costs must fall, and plants must be safe and reliable. But the direction of travel matters. When a field moves from one giant project to several competing builds, learning speeds up, and every breakthrough pulls more talent into the field. And that is what makes this moment feel different. For the first time in a long time, fusion progress is not just a promise, it is a race. Fusion has always been the ultimate maybe. It asks us to build a star and keep it on a leash. But the story is shifting. The giant international reactor in France still matters because it proves what is possible at scale. At the same time, smaller private teams are using stronger magnets and faster build cycles to close the gap. Whether the winner is a government project, a startup, or some mix of both, the real victory will be a new tool for clean power. Until then, every weld, coil, and test shot brings the sun a little closer here.